Okay, so I thought I'd graph this on Desmos to show you the graph that we've been talking about. So here's sine x over x, or sinc x, and we've drawn it for a range of, I think that there's 3 pi's, we've got up to 4 pi here, and minus 4 pi's here. So you can actually see on this graph, if you look very carefully, that the peaks are not exactly at minus 3 pi over 2 and 5 pi over 2, or minus 5 pi over 2 and minus 3 pi over 2. They're actually shifted a little bit closer to the origin. And what shows that even clearer here is if I add the lines of 1 over x and minus 1 over x. So you see these two dots here, they actually show you where the graphs touch, but also the maxima and minima. And you can see each time these dots actually get a little bit closer together. So you can see them as almost like two distinct dots here, and here they're a little bit closer. And if I moved down the graph, I can see here those two dots. Where did they go? Maybe if I zoom out a little bit. There, that's better. Here those two dots get closer and closer together. And that's what we've been showing. Okay, so that's very interesting that these two dots get closer together, and we can show that. And then I can prove it to you using Desmos. Okay, great. So you might have noticed here I've got y equals sinc squared x and y squared is equal to sinc x. So these are some graphs that I might get a student to draw if they found this one easy. So I would first ask them to draw this graph, see if they can reason that the limit as x approaches 0 is in fact 1. Then I would ask them where exactly these peaks and troughs are. Do the peaks and troughs get closer to their, get closer to the minus 3 pi over 2 and 3 pi over 2, or do they get further away? Okay, and obviously they get closer together because we just argued that. But then if they find all of that easy, then what am I going to do? I'm just going to make it a little bit harder. So if I make it a bit harder, what I would do is first ask them to draw y equals sine x over x, but now all squared. So let's have a think about what that will look like, and we can go back to this graph to this graphing calculator at the end and put on this curve and see if we were in fact right. So I'm going to go to a fresh page here, and I'm going to first draw my graph of sine x over x, because we're going to use that as our basis for drawing what that graph curved would actually look like. So here's an x-axis, a y-axis. We're interested in the points pi, maybe 2 pi, 3 pi, and we can also talk about the negatives as well, because we know this is going to be even. Okay, so we said that it crosses up here at 1. So this point here is 1, not negative 1, 1. And we want to draw a little ring around this point just to show that it's the discontinuity. It's actually undefined at this point here. So drawing this curve down, I know it goes through pi here, and then the peak is going to be slightly closer to 0 than it should be, well, not than it should be, than is symmetrical about this point minus 3 pi over 2, and so is this one. So something like this would be good. Okay, that is a decent drawing of it there. Okay, so again the peak's slightly closer on this side, and again peak slightly closer over here. Okay, so I've only drawn it up to 3 pi and down to minus 3 pi, but the first thing that you might want to ask yourself, if you're going from y as some function of x to y is actually that same function of x, but now that function of x is squared. Okay, so now I'm trying to draw this. Okay, for the case where the function of x is sine x over x, is which points would be invariant under squaring this? So which x values or y values, when I square them, are actually just going to stay the same? And there are only two numbers for which when you square it, it remains the same number, and that is 0 and 1. So you can think of this as, this is my old function of y, or I could call this sort of y1. And now I'm actually drawing the curve of y equals y1 squared. Okay. So I said that only at 0 and 1 will this curve be in exactly the same position. And that's true, right? If I put 1 in here, I square it, I get 1. If I put 0 in here, I square it, I get 0. So what we can say immediately is that our curve is at the same points at 0 and 1. And we will still have a discontinuity. So just in the same way that sine x over x you can't put in 0, you can't put in sine x over x squared either. If you do sine x over x squared and you still put in 0, that's still 0 over 0, but you're squaring it, so it's still undefined. So I can draw this circle around this point here, and I know that it still crosses at all of the positive and negative whole number values of pi. But something else that I might want to consider is what happens to a negative value when I square it. Well, a negative value when I square it becomes a positive value. And I've had a lot of students try this question, and immediately what they do is they say, okay, so it's this. Okay, so here it's just like this. You just reflect it up, and the rest of it stays the same. And that might seem smart to answer quickly, to sort of be timely with your answers, but don't do that. Okay, don't be too quick to answer. Think things through slowly. So there's a problem with this, and that's actually that the gradient is discontinuous at this point here. So any time that you have a curve that kind of comes to a point, to a sharp point like this, how do you tell what the gradient is here? You can draw so many tangent lines to that point that it's not actually differentiable at that point. And if you think about y equals sine x over x and then squaring it, that should be differentiable at all points because x squared is differentiable and sine squared is differentiable. I mean, it just doesn't really make sense. The only things, the only thing that can make sort of a function differentiable is sort of an abrupt change in its behavior. So in fact, what you're drawing when you're reflecting this in the x-axis is you're not drawing it squared, you're drawing the modulus. Okay, you're drawing the modulus of that function, and those two are not the same. So don't rush to that conclusion. We'll get rid of these bits on the graph here. Instead, think about the size of the function. So at 1 and at 0, we said, yeah, it stays the same. But everywhere else on this curve, we have a value that's between, well, actually, let's use minus pi to pi first. Just talk about where it's positive. We have a value that's actually between 1 and 0 in this range, between minus pi and pi. So whenever you square a number that's between 1 and 0, you actually get a smaller number. Think about a half. A half squared is a quarter. A third squared is a ninth. So you've got this idea that actually all these points will be reduced. Okay, all these points will be brought down. And if you're actually at something like 0.9, 0.9 squared is, hard one. But it's going to be reasonably large still. It's going to be 81 over 100, so it's 0.81. So the sort of reduction or percentage reduction in the size of these values gets greater as you approach 0. So you're going to get a curve that kind of looks like this. Initially, it's going to go down steeper than this curve, and in fact you're going to go to 0 like this. Okay, so you will curve to 0 at this point here. You could actually differentiate this function y equals sine x over x squared and prove that all of the points pi, minus pi, 2 pi, they're actually minima now. They're minima of this curve now. So if we do this on both sides, it's still going to be an even function. An even function squared is always an even function. So something like that. That's going to be a minima. And then when you square this, it's not going to go up quite as high as it used to. And actually, maybe we should consider, is the maxima still going to be shifted over slightly? Well, yes, because if the maxima is here, really all we're doing is squaring this number. So the maxima here, when you square that, it's going to give the largest number for the red curve as well, the sinc squared function as well. So it's still going to have this kind of peak shifted over to one side, and actually all these curves are going to be even smaller. So I would draw something like this. Okay, it shouldn't go below the axis, but I'm just trying to draw it very, very small there. All these peaks should be tiny now. Okay. So why did I get you to draw this curve in particular? Or why would I get you to draw this curve in particular if I was doing a mock interview with you? Well, if you're doing, if you're doing physics or maybe even chemistry, you might have heard of diffraction or the double slit experiment. And this is what the diffraction pattern looks like on the screen. I often actually say at the beginning, this sinc function, and sinc squared in particular, is a function that's used in physics a great deal. And that's why it's got this particular name. And it's used in optics, or I say it's used in a diffraction experiment. And at the end, I get the student to interpret it. So I'll see if they can link this to the maxima and minima that you might see in a diffraction experiment. So in fact, this would actually be a graph of the intensity and against some sort of coordinate on the screen. So if this is the position of the central maxima when you use a double slit or a diffraction grating on a screen, then these will be the positions of the subsequent maxima, so the nth order maxima. Okay, and it's not exactly x; it's just distance, because it has something to do with the it has something to do with the wavelength of the light you use and the distance in between the slits and the size of the slits. So you have to just say that this is some coordinate. It is proportional to the distance, though, from the maxima. So for x being some unit, for some wavelength of light and some experimental setup, this is what you would get. Okay, cool. So if they correctly answered this part of the question, just for fun, I might get them to do now, even harder, can they draw the curve of y squared equals sinc x? Okay, y squared equals sinc x. So this is not so easy as the last one, and nor is this function so useful in physics, but it is interesting to see if they can reason as to what this graph would look like. And usually my students say, oh, well, immediately what I can do is this. I can square root both sides of the equation, just say it's the square root of sinc x. But almost invariably they'll forget about the plus or minus. So when I give you an equation with something squared in it, when you square root it, it is in fact plus or minus. So I find that actually a lot of good A-level students still don't really know when to stick in a plus or minus or not, so they do it a bit haphazardly. So in general, you can put a plus or minus in, or you need to put a plus or minus in, if you've been given an equation with something squared and you're going to take a square root. So if I say to you x squared is equal to 9, then when you take that square root, you do need the plus or minus, because it could be plus or minus 3 that solves this equation. But if I said to you, well, I don't know, something like x equals the square root of 9, you don't need to put plus or minus in, because I've told you in the question that it's only the positive root of 9. Okay, so we'll see some more problems that use plus or minuses and maybe square roots later on. I'm going to do a series on kind of infinite expressions and infinite series and things like that, because infinity comes up quite a lot in these sort of interview questions, just to complicate things that you haven't seen before, just to sort of make students think about what happens as series tend to infinity and things like that is usually a very useful tool to measure if they're actually going to be any good at an undergraduate degree in physics or mathematics or engineering. So let's consider this curve. If we actually did look at the square root of sinc x, what would it look like? So again, this is one that is invariable about these values of minus pi, 0, pi, because when you square root something, if you square root 1, you still get 1, and if you square root 0, you still get 0. So again, we can say, I'm going to take a new color now, let's take maybe green. You can say that you're still going to have a discontinuity here. Okay, it's going to remain at that point, and it's still going to give 0 at all of these points. Okay, because if you square root 0, you get 0, and if you put 0 over 0 into sinc x, even if that's underneath a square root, you still have a discontinuity. So I'm going to plot all of these points again. Now the next thing I'm going to do is consider the size of the function. Okay, what is the size of this function? So in fact, this function is less than 1 throughout this range of pi to negative pi. And when you square root something less than 1, you get something slightly larger, right? If you square root a quarter now, you would get a half. Okay, so I'm actually thinking about square rooting the blue line here. So in fact, it's going to have to maintain, it's going to be a bit bigger than the blue line the whole time. So if you square root something like 0.1, you're going to get something quite a lot larger. So it's going to have a shape sort of similar to this. Okay, and in fact, it shouldn't ever duck below the blue curve like I have done here. And I think it's going to approach a maximum at the top here again and come back down here. But remember what we said about it being a plus or minus. Okay, it's a plus or minus, this curve. So in fact, it could be any of these values down here, and you'd have another discontinuity at -1, and it's just going to be a reflection in the y-axis, something like this. Now, these weird oval shapes, these weird green blobs that I'm going to draw, there's going to be more than one of them, but the next thing you need to consider is, can you draw another green blob here like this, or can you not? Well, let's think about that. What is the value of sinc x in this range? It's negative. Can I do the square root of a negative number? No. Or I can't if I want a real solution that I'm going to plot on the xy plane. So this curve does not exist anywhere where sinc x is negative. So it doesn't exist here, doesn't exist here, and it won't exist past 3 pi and past minus 3 pi to minus 4 pi, or 3 pi to 4 pi. Okay, so it's only going to be, you're only going to get these sort of blob shapes every so often. Okay, so there'll be another kind of blob here. Okay, it's going to be higher because we know that we're square rooting this value. So whatever this is here, it's negative. It's less than 1. So when I square root it, I'm going to get something slightly larger. In fact, I think we said our root here is minus 2 over 3 pi-ish, something close to that. So when I square root that, it should jump to quite a lot higher. Sorry, it's not minus, and that's not the, that's the y value here. So it's 2 over 3 pi. Okay. No, what am I talking about? It's 2 over 5 pi. Okay, that's our 2 over 5 pi root. Our 2 over 3 pi, our negative 2 over 3 pi root doesn't exist. Okay, so again, it's going to be a curve that is symmetrical about the y-axis, and these blobs aren't going to be in the range where sinc x is negative. Now, if a student did all of this very, very well, which is vanishingly small proportions of students actually can answer all of these questions correctly in a timely fashion, then I could always complicate things. I could ask them to find me the gradient whenever it crosses the x-axis. And that's something that we could talk about in the next video, how we would find the gradient of this curve, because it uses a technique that that I haven't actually talked about yet, which is implicit differentiation, but it's something that's quite useful in a lot of Oxbridge interview questions. Okay, thanks.